For this FRQ, we have a graph of the derivative, and for part A, we're looking for g of 3 and g of negative 2. So conveniently, we're given g of 0 equals 5, so we'll use that, because g of 3 is actually g of 0 plus the accumulation, or the interval from 0 to 3, of g prime of x dx. We know g of 0 is 5 because it's given to us. The integral from 0 to 3, we'll just find the area under the curve of this graph of g prime. So from 0 to 2, we have a quarter of a circle here. The area of that is 1/4 pi times r squared, r is 2, plus from 2 to 3, we have this triangle. And the area of the triangle is 1/2 times our base of 1 times our height of 3. So we have 5 plus this right here, simplified to pi, plus 3/2. If we think of 5 as 10/2, we end up with 10/2 plus 3/2, which is 13/2 plus pi. So that's g of 3. For g of negative 2, we'll start with g of 0 again, but now we're going to go backwards, so kind of reverse accumulation, subtracting the integral from negative 2 to 0 of g prime of x dx. And g of 0 is still 5, same problem, minus, now the integral from negative 2 to 0 starts here, goes to here, is actually just the other quarter of the circle, and we know the area of that is pi. So g of negative 2 is just 5 minus pi. For part B, we're finding points of inflection. So point of inflection, our graph is g prime, and the point of inflection of the graph of y equals g of x, any of those will occur basically when the second derivative changes signs, which is basically just the rate of change of g prime. So we're looking for when g prime of x basically goes from increasing to decreasing in terms of a rate of change, or decreasing to increasing. So like the slope of the tangent line, or the slope of the tangent line of g prime. So looking at our graph, let's look at it. Let's start at negative 7. G prime is increasing until it gets to 0, and then it starts decreasing. So there's a point of inflection. I suppose we should have a sentence, right? There is a point of inflection at x equals 0 because g prime of x goes from increasing to decreasing. Okay, going back to 0, now it's going to decrease, and then it goes from decreasing to increasing at x equals 2. So there is a point of inflection at x equals 2 because g prime of x goes from decreasing to increasing. Going downward and then going upward. And now at 2, it'll increase until it gets to 3, and then it'll decrease until the end of the interval. So at 3, there's a point of inflection because it goes from increasing to decreasing. So last seems too long sentence. There is a point of inflection at x equals 3 because g prime of x goes from increasing to decreasing. Part C. Now we have another function. Great. H of x equals g of x minus 1/2 x squared. And we're looking for the x-coordinate of each critical point of h. And we'll classify them as relative min, relative max, or neither of those qualifications. So if we want critical points, we'll have to take the derivative and set it equal to 0. So if this is h prime of x will be, well, the derivative of g is g prime of x, which is convenient because we have a graph of that, minus the derivative of 1/2 x squared is just x. If we set that equal to 0, we're essentially looking for where g prime of x is equal to x. Okay, so in our graph up here, essentially our x-coordinate is x, and our y-coordinate is g prime of x. So we're looking for when the x-coordinate equals the y-coordinate. So these are all negative and negative, but none of them are close to -7, -7, -6, nope. If we look around here, these are negative x's, positive y's, that won't work. Looks like somewhere in here we'll have a point that should work. So at that point between 0 and 2, our g prime is actually, since it's a semicircle, the positive half of it with a radius of 2. It's the square root of 4 minus x squared. And we'll set that equal to x. If we solve that little equation, if we square both sides, we get 4 minus x squared equals x squared. 4 equals 2x squared. So 2 equals x squared. So x equals the square root of 2. There's one of our critical points that we've now found. When I took the square root of 2, I only used the positive part. I did not use negative square root of 2 because we're only looking here on the graph when the x value is positive. Let's see if there's anything else. Well, 3, 3. That's definitely true, huh? So at the point 3, 3, g prime of x, which is our y-coordinate, equals x. So x equals 3 is another critical point. Okay, so now we'll test them and see if they're relative minimums, relative maximums, or neither. So we'll make a little, table. So h prime, well, I'm going to erase here. H prime of x, which is equal to g prime of x minus x, and we'll also look at x. So we know that h prime of x is 0 at square root of 2 and 3. So now we'll test around these. So if we look at somewhere less than square root of 2, let's go for, 0. Why not? So at 0, that's the point 0, 2. And so g prime of x, which is our y, minus our x, would be 2 minus 0. So that will be positive. Now let's try in between square root of 2 and 3. So let's say 2. At 2, well, g prime of x is 0. So 2, 0. Again, g prime of x minus x will just be the 0 minus the 2. So that's negative. Now let's test greater than 3, or to the right of 3 if we're thinking of our x values on the graph. Let's do 5, -1, because we have that point. And so then g prime of x minus x will be -1 minus 5, which is negative. So the only place h prime of x changes signs is right here at x equals square root of 2. So then we know that h of x has a relative maximum, because we kind of follow the curve, relative maximum at x equals square root of 2, because h prime of x goes from positive to negative. H of x has neither a relative min, or rel min, because I'm, don't want to write it all, nor a relative max at x equals 3, because h prime of x does not change signs.